This video is on the use of R in hypothesis testing. Let's begin with the idea behind hypothesis testing. What I'm listing here are the variables that you will use in R. You can call them different names, but I'm going to just list them here with these names so you have them all in one place. In hypothesis testing, we start with some old or previous or formerly held idea. And since we're talking about numbers here, we'll talk about means with numbers. Say we have a factory that manufactures clothing, and we think that our seams are 5/8 of an inch. Okay? Or the average seam is 5/8 of an inch. This is what we call mu naught. This is our previously held idea. And it is the mean, and it makes up the null hypothesis. Okay, I'm going to call it mu naught. You can call it something else, but I'll just stick with this notation for right now. Then some testing happens, and the mean of the testing is different. And here is the mean value here. Let's say we do testing on these articles of clothing that we make, and it shows that our seams are 6/8 of an inch. So this is the mean from the sample, from the testing. Another important parameter is n, and that's the size of the sample. That's how many articles we tested. We could have tested 25, we could have tested 250. That's what n is going to be equal to. Now we need some standard deviations. SD0 I'm using as a standard deviation of the population. This would be the standard deviation for the previously held idea. Say an incredible amount of testing was done before, showing the 5/8 of an inch, and it had a certain standard deviation associated with that testing. That would be your SD0. Okay? That may or may not be available. Now here's a standard deviation for the test, or the sample, SD test. I'll write it like that. The standard deviation SD0 can be computed from SD test and the size of the sample. Here's the formula. This is all statistics, so it's all approximate. We can go like this. SD0 equals SD of the test divided by the square root of n. That's an estimate of SD0. You'll see this formula, this fraction, somewhere else as well. The next thing we may need to do, is to normalize the mean for the test. By normalize, I mean put it in the standard form. If you're using a normal distribution or a t-distribution, this means a mean of 0, okay, and a standard deviation of 1. So if we want to put it in that form, we create what we're going to call z-test or t-test. For the normal distribution, you don't have to do this. You can use your original numbers. For the t, it's required. So how do you use the original numbers? Say you're looking for a probability with a normal distribution. So you want the probability that the number 10 will occur. If you write after it mean equals, say, 14, and SD equals 0.25, then you use your original numbers. If you don't want to use the original numbers and you normalize, then you don't have to specify mean or standard deviation. However, you can't use the 10 just as it is. You have to change it into the z-value. And once you've changed it into the z-value, then all you do is, that's supposed to be an O, norm, and I'll just put the z-value here. Oops, I'm sorry, and that's all you have to do. You're done. Okay. For the t, you absolutely have to change it. You don't have this option to specify mean and standard deviation in a t-test. So after we have all our data and all the required numbers, then we decide how confident we want to be that we're either accepting, in our example, the 5/8 inch seam and assuming that everything's fine, or we want to reject that null hypothesis and maybe have the machines recalibrated. So we have to decide the confidence level we're comfortable with, and of course we typically are using in this class 3 confidence levels: 90%, 95%, or 99%. These correspond to alpha values. We're looking at alpha now of 0. Whoops, sorry. This is 0.10, this is 0.05, and this one is a 0.01. So we specify the alpha, and in R we can specify all 3 alphas at once by creating a vector, and I'll go over that, and you've probably seen that already. Once we have the alphas, remembering what they are, alpha is really the area of the tail that in a sense you're rejecting, or you're calling your critical region. Right? If you're doing confidence intervals, you're rejecting the tail. Here we're going to call that tail the confidence, or the the critical region. Right? And we'll need to know the value along the horizontal axis that's right at the edge of that region, and that's what we can call T alpha if we're using a T distribution, Z alpha, or you can just call it CV. Alpha and these T alpha, Z alpha, and CV make more sense when we look at them graphically. So here's an example. This is of a normal distribution, standard normal distribution. I think that's spelled wrong, but alright. So this is the standard normal distribution. That means everything's been normalized to a mean of 0. Here's the 0, and a standard deviation of 1. Right in the center of this, that mean of 0, is our mu naught 0. I was writing it as a variable, so I go mu naught instead of the Greek letter mu. Okay, that's right here at the middle. What I put as k in this graph is really our z test value. Obviously, this is a left-handed test. Right? So the alpha is 0.1, means that the area that's shaded in here has an area of 0.1. Recall that the area under the entire curve is 1. Right? So starting here and going out is 10% of the area, but we don't really know where that is until we run z and we find our critical value. In this case, it's minus or negative 1.28. You could also call this z alpha if you wanted. Our critical value works fine too. So now we know the edge of this. The z-test gives us another point here. And the idea in hypothesis testing is that if this z-value is located in this critical region, which is shaded, then the null hypothesis is rejected. If that z-value happened to be located out here, closer to the mean than the critical value is, then it's in the non-critical region, which isn't shaded in this picture, and the null hypothesis would not be rejected. You would be saying the new measurement is not statistically significant. Okay. Let's look now at a left tail test and the sort of thing that you're going to be getting from R. This is the output you will probably be getting from R. This is a normal distribution. I didn't put any notes on it. So this is a normal distribution. Notice this is not standardized. It's not a standard. How do I know that? Well, the mean is not 0. Okay. In this graph, I only printed out part of the bell-shaped curve. And I'll discuss that a little bit when we get to the plotting. Okay. In this example, which is what you're going to be doing with in R, there are 3 critical values. Okay, they're shown here. Here's 1. Here's actually I called this 1, this 2, and this 3. They correspond to 3 different alpha values. Okay. Remember, alpha is the area It'll be the alpha in for 1 will be the area from here all the way down into the tail. Okay, that's a fairly big area, and this is an area of 0.10. For the green one, I think I can change color here to make it color coordinated. Would start at the green and go all the way into the tail. That's a critical value at the edge of a region that has an area of 0.05. And the last one, obviously, or maybe not so obviously. Okay, I can't get the pen to change color. We'll just forget about, oh great, color coding. Okay, so that would be the area going under here, going all the way down out into the tail, and its area would be 0.01. So you see there's selectively smaller areas as you move into the left tail, and that makes sense. Now, the test value I've shown here in dash line. I'll give you the command to do that in R in this tutorial, but there's so many commands in R and I don't give you all of them. Otherwise, we'd spend all our time just doing R. Okay, here is the test value. This is the, well, it's not normalized, so all this is mu for the test. I didn't normalize it to z value. And now we can look and see where it is with respect to the critical values. In this case, for every single critical value, it is not in the critical region. It is in fact closer to the hypothesis testing, the null hypothesis, the mean associated with the null hypothesis. All right? In this case, the null hypothesis would not be rejected. At what confidence level? Well, the first one is for an alpha of 0.10. That's a confidence level of 90%. So it wouldn't be rejected there, or at the 95%, or of course at the 99% level. Let me erase the screen for a second. Okay, and now let's do a different. All right, here's a line, and let's say this line happens to lie here. That's a pretty big line, but that's going to be, I had to do that for emphasis. All right. Okay. Oh, forget that. Say this was the mu. I'm sorry. I'm write it like this for you for the test. And here's a critical value for, this is a critical value here for a 90% confidence level. Here's a critical value for 95%. And here's a critical value for 99%. Okay, forget this over here. I'm just trying to show a different case. All right. Now, for the 90% level, or alpha equal to 0.10, this test value lies inside of its critical region. Okay, so at the 90th percent confidence level, or you could say alpha equals 0.10, the null hypothesis is rejected. Now if we look at the 95% confidence level, so this would be your 95% confidence level, your alpha is 0.05 for this left tail test. Again, the test value lies in its critical region, so again the null hypothesis can be rejected, of course with a certain confidence level of 95%. Now look at the third case. For the 99% confidence level, and this would be alpha equal to 0.01, the t, or the test value lies outside of the critical region. So for the 99% confidence level, alpha equal to 0.01, H naught is not rejected because the test value lies closer to the mean than does the critical value. Here's another example using for a right tail test, and if we put the confidence or the test value right here, okay, then this is the 90th, here's the 95th percent, and here's, does that say percent? 99th percent confidence level. So at the 90% confidence level, the null hypothesis is rejected. At the 95 and the 99% level, it's not rejected. Okay, now I'm going to go to R and show you how to put these commands in and how to get the graphs. Okay, here I am in R, and I want to point out something. If you have saved a previous workspace, or you've done a calculation previously and named it, for example, alpha, R remembers alpha until you redefine it. That sometimes causes problems. Okay, so we're going to start here and do a normal distribution, and we're going to use the example of the rivers, which is saved data in R. And we have to start off with a previously held idea, a previously held mean for the length of rivers, and we'll say that's 640. So we have to tell R that. Now I'm going to look at this data, rivers, and you won't be able to see all of it in the screen because I made the typing bigger so that it shows up in these videos. Okay, so there's a bunch of data stored here. These are links of a bunch of rivers. I'm going to need the mean from this testing or this sampling. So I'm calling it, and all I have to do is take mean of rivers in this case, and let's take a look at it. It's always a good idea to look at what you get. Okay, 591. Now the previous one was 640. Now we're down to 591. We can call this a left tail test because the new value is less than the previously held value. We also need to know the number in rivers, and even though you think you could count it, it's a good thing to get it, and you just use length. And again, it's a good idea to take a look at it. 141, that makes sense. Right. Now I don't have any standard deviation associated with that 640, but I can get the standard deviation of this data. You can use equal, and there's also an assign, and you can use either one. So I'm taking the standard deviation of rivers, and let's take a look at it and see what it is. Oh, that's fairly large. Okay, I'm going to compute the other, the scaling into using the number of samples, which is the 141. Okay, and that would be take the test divided by the square root of m, and the command in R, as you probably already know, is sqrt gives you square root. And let's see what that looks like. 41. Okay, so that makes a little more sense. I'm going to run through this one, not normalizing, just to show you, because I want to point out a few things. Okay, so now we have those. That's the first part. I'm not going to normalize, so I don't need a z-test value. I'm not going to use it anyway, but I could do it if you want it. It just looks, well, I'll do that later. Okay, now I need some alphas. I want to check 3 different alpha levels, so I can put them in vectors. I'll do that 0.10, 0.05, and 0.01. C is to concatenate or concoct this vector. Oh, I called it alpha instead of alpha, so just space back over, and here we go. Let's see if alpha made sense. It did. So I got out what I needed in alpha. And now I'm going to need some critical values. So I'm going to call them critical values. Okay, I want to make a note here just because it doesn't hurt to repeat things. So let me get a pen. Right. The base of the distribution has a name. We're using normal distribution, and its base is norm. Prefixes go in front of it that give you different information for this normal distribution. If I put a P in front of it, then I get a probability. If I put a D in front of it, I get a value right on the curve, the distribution curve. If I put a Q in front of it, then I will get one of the horizontal Z value, actually, or in this case it's not normalized. I'm going to get a value along the horizontal axis that corresponds to an area to the right of it, unless I specify lower tail equals false. Okay, so what I'm going to do here, I'll erase that, is the alphas give me the area. I need the value right at that edge of the area, so I use Q norm, and when I give it the alpha, it takes all of them at once. Right? This is not normalized. This is going to be a curve that doesn't have the mean at 0 and doesn't have a standard deviation at 1. I'm going to use just the data numbers, and because I'm going to do that, I'll have to specify the mean, and the mean is going to be, okay, and a standard deviation, which will be, this will set up the curve. Okay, so let's see what our critical values look like. Now, right from here, we'll be able to tell whether, or for which cases, the null hypothesis is rejected or not rejected, but we're going to go ahead and do the graph. This is sometimes a troublesome point in creating graphs, and this is picking the values or the maximum and minimum values that are going to lie along the horizontal axis. Right, this is not normalized. It's only a left-tail test, not a two-tail test. It's left-tailed. So all I really care about is from the mean all the way down into the tails. So what mean is going to be right at the middle of this? It's going to be the mu0, which was, no, I can't scroll off of it. Sorry, it was 640. Okay, let me draw it. Okay, so we're going to have a curve that's going to look something like this. Right in the middle of it is going to be a 640. Now these critical values are going to show up, and one is at, here's a 580, here's one at 571, and here's one at 543. I want to be able to draw all three of those. I would also like to be able to draw the t-test value. So I'm going to go back and find that. Oh, it wouldn't scroll back. Okay. Well, the t-test value isn't any lower than the 543. So let's go a little bit less than that, and we'll start at 500. So if we draw the curve from 500 up to 640, we will see the peak, we will see all the critical values, and we'll be able to plot also the new mean. On some of the videos and in the tutorial, you might see a command that looks like this. Okay, what does that give you? That's going to give you, let me pin back here. Okay, here's my horizontal axis. Here's the 0 on it. Here's a -3. Here's a +3. Where was my curve? It had a mean out here at 640. What do you think it's doing between 3 and -3? Absolutely nothing that the computer can even see. So if you pick those values, you're out here in the tail and you won't see anything. And that's kind of a common mistake because there's not an understanding of what these numbers mean. This is the lowest X horizontal axis value, I'll say that, we're calling it X, and this is the greatest one. So make sure you capture your region of interest. So instead of this command, if I can still use 100 points. the smallest number is going to be 500, and the greatest number, let's go a little bit over, say 600. Okay. Also in R, the command pretty, you're sort of giving R permission to fix it up any way it wants. If you print out these X values, you might be surprised at what you get, but somehow it works. And if it doesn't, just try some different numbers. Let's just do 50, and I want to show you these X values. Okay, see, it starts at 500 and ends at 600, and R kind of spaces it out in between to give you 50 points. Now let's go get the values that will be on the y-axis. The values on the y-axis we're going to get from the distribution curve for the normal distribution. So it's a D because you want the points on the curve, and it's a normal distribution, and we want them associated with every X value. So these are the X values, 500 to 600. What am I doing? I needed 640. Okay, that's good, I saw that. So let me fix it up. How do I fix it up? I just go backwards till I get the command I want, and we'll go to 6. Well, we'll just go 650. Okay, and let's look again. Yes, you see it went and pulled it all over to 650, although it seems like it didn't give me so many values, and that's R working, but I think we'll be okay. So this is going to be distribution values from the normal curve associated with the X values we've given. This is again not normalized, so we have to specify the mean and the standard deviation, and now we have X and Y values. So when I go to plot, I plot X, Y, type equals, we want a solid line, so that's L. Remembering that's the letter L, not the number 1, although in different fonts it can look like the number 1. That's L, little lowercase letter L for line, and we'll give it a color because it's going to be the curve. Okay, and let me move that curve over into the region here, and there's our curve. You see it's going, I didn't give any labels to it, and that's okay. It's going from 500 up to 650, and so the mean is captured in here, and we'll be able to put our critical values on. So let's go back to the screen here, and now to put the critical values on, we use AB line, which is a command that will draw a line on the screen. We want a vertical line, and we want it at the critical value, and the critical value is a vector and has 3 values in it, each one associated with a different value of alpha, and it's numbered from 1 to 3, not 0, 1, 2, which I like to do, but it's 1, 2, 3. And to get the first one, we have to use double brackets, put the number of it, and we'll give it a color. This one will do red. Well, do that properly. And now we have to go find, just a minute, I'll go find the graph. So here is the graph. It's the same base graph we have showing that normal distribution, and we've got one red line at the first critical value. Now we'll go put the rest of them on there, and we'll look at that again. Okay, so I just have to repeat this AB line command. We'll give it a different color and select a different one of the critical values. Okay, that'll work. And we need another one. Make this one blue. And this would be the critical value 3. So now we should have 3 critical values on there. And now we need to put the test value on there. And that was, remembering that R is case sensitive, so if we put a lowercase t, we won't get anything. We might get an error though. Okay, what color do we want it? We'll just go back to the one for the graph. We'll call it black. But in order to see it, and you don't have to do this, but you can go LTY equals 3. That will give you a dash line. I hope you can see that on here. Let me move this a little bit. Okay, LTY, line type, if you want to use that command. Alright, Now we'll go look at what we've got, and here it is. Well, I went to Windows and got hold of it, and it didn't want to move where I wanted it to. Here it is. Okay, so you see the normal distribution. You see the three critical values in different colors showing up. And then because I used LTY equal dash, it does make the test values show up. Okay, that's an example for the normal distribution, not using it not normalized. I'm going to quickly run through how you would normalize this if you want to do it. First, you're going to need a z-test value. So to do that, you subtract the two means and you divide by, well, I'll write it like this. Okay. Now you see the z-test looks sort of reasonable instead of with those other numbers. Alright, you have your same, you want your critical values again. So critical values, these are going to be normalized, so I'll call them z-alphas. Again, I use Q norm. The alpha is the same, but I don't specify the mean or the standard deviation, and it will pull those alphas in from the mean of 0, standard deviation of 1. And so here's my critical value again, and now you see how they look compared to the z-test values. Okay. What happens if you put lower tail equals false on there? You will get those critical values as though they were on the right side, and you'll have a big sign problem if you do that. So remember which kind of test you're doing. Left tail test, do not specify lower tail. Okay. Now I need some some x values for my plot. Again, I could use pretty, and if I look here, I'm going to want to go to 0 and down to like minus 2.3. That's the lowest number. So let's go minus 3 to, let's say, 0.5 and give it 50 points. Check out x to make sure it's reasonable. Okay, now go get the y values, which would be the distribution on the normal curve for those x values, and you don't specify anything else. Okay, just using the default, and now we can plot these. Oh, sorry, type. There's columns. And we can put the same AB lines on there, but we're going to have, I'll just put one on here, which would be your Z alpha. Let's just put the first one. And we'd also want to put on there the z-test value. So it's an alpha, we'll put, and let's see what we got. Now you can see along the x-axis, we're going from 0 at the peak. It didn't quite come out right, but it's in a little bit. I don't know why. Oh well, that's what R did. And it went down to minus 3. Here was that first, in red is the first critical value, and then here's the test value. I didn't change the line type. That's now normalized. Now I'm going to run through a similar example, but I'm going to do this for a t-distribution. How do you decide when to use a normal and when to use a t-distribution? It has to do with two things: the number of points that you have, and also the instructions. Some examples that you're given for homework will not have very many points, but the instructions will say use a normal distribution. That's just to learn about normal distributions. But if you're doing this for real, not just for homework, and you have to decide, you look at the number of points, and that makes a decision. So right now we're going to do the benzene example. It's in the textbook on page 351. Okay, So first we have to specify the, the mean associated with the null hypothesis, and in this example it happens to be 1. Okay, then we have to get some values in. They aren't stored. All right, since they're not stored, I have to enter them. So first I have to tell what benzene is going to be. It's going to be a data frame, and it will have some sort of a variable. So you say content equals, and it's numeric. Okay, but you know how to create that already. Then I have to put some values in benzene. So I'm going to do fix okay, and it will open a new window, and I get to enter some values. Alright, I'm entering them here, and you can see my variable content is already specified, and I'm just going to enter them, but to make the video shorter I'll turn off the video now and enter the rest of. So now I've entered all my numbers under using the fix command, which opened my data entry window, and sometimes a question arises, how do I get these into R? And you do it in a rather unceremonious way. All you do is close the window and they're stored. Wait a minute. Right, we're gonna have to try this again. I hadn't scrolled up, so I closed all of R down. Alright, so now I've entered everything here, and I have to move this window over and close it. So here I am closing just the fix window and not all of R. If you do that, it's not the end of the world. You just get to enter everything again. I'm moving R back over so you can see it on in the video, and let's see what's in benzene. There it is. Okay. So it's the numbers that I entered, and you can see these in the textbook. Now we go through the same steps. What's the test value? And this is a little different. I need the mean. Now benzene I put as a data frame. If I haven't attached it, then I have to specify the variable, and it's done like this. Well, first you spell it right. $, and the name of the variable, which I called content. See what I got? Okay, 2.144, which is significantly greater than the mu naught. If you remember, mu naught was set at 1. So it seems to be different. We don't know how it is in comparison to the in our hypothesis testing. Now we need the number. It's always good to calculate it. And it should be 20, and it is. Okay. The standard deviation we don't have from the test, but we can get it from the data. SD, again, benzene. Okay, if you're tired of doing that, you can go. Alright, now I can go. Okay. Alright. This is going to be a t-distribution, so absolutely have to normalize it. And its formula is the same. You take the mean for the test from the test minus the original divided by let me pull this over so you can see the entire command. Okay, the mean for the test minus the original mean associated with your null hypothesis divided by standard deviation for the test over the square root of n. Use enough parentheses, otherwise you'll have an algebra error. The alphas have been stored because I already did a calculation, so we'll just see if they're there. If they're not there, they're fine. Otherwise, I'd set them up again. Okay, now I need some T alphas, which are critical values. So we're going to use the QT. T distribution, Q means go over that amount of area and go up to the curve and find out the horizontal value associated with that area. All right, so it's going to be the alphas. All right, now this is T distribution, so we need degrees of freedom. All right, now I'm going to go to the next line, and if I don't finish the command, remember it goes down here and it says more needs to happen, so it gives me the plus sign instead of the greater than sign that it usually uses for at the beginning of the lines. So now I have to fill in the rest, and the reason I did it like this is so you could see what I'm going to do next. And this is a right tail test. Everything's going to be on the right side, so I expect critical values to be positive because they are greater than 0. So I have to specify lower tail equals false. Okay, let's see what T alphas we got out. Alright, they're all positive, and that makes sense. Now, the mean, this is normalized. The mean's going to be 0, and I'm seeing here a 2.539 for my greatest critical value, and the mean for the test was about 2.41, so that's going to be the biggest number I want to see. Now I'm setting up my x-axis using pretty, and we'll start at 0, it's fine, and we're going to go out 2.5, so we'll go out to 2.75, whoops, it's a colon here, so that's the smallest value on the x-axis of the graph, and we'll give it 50 points. Let's see what we got. Alright, that looks like it's about right. 2.75, yeah, that's probably worked out okay. Now I go get some y values. I need y values from a T distribution. That will be D, meaning on the distribution, T for the T distribution, and I give it the x's, and now it's a t's again, so I have to give it again degrees of freedom, and that's all. Now I have x and y's, and let's go ahead and plot them. X, y, make it a line, and give it a color, something. Oops. Okay. Let's put our vertical lines on here, and they're going to be at T alphas. Remember, it's whoops. Vertical line, T alpha, double bracket, first one, and give it a color if you want. We'll make the next one green for no good reason. Well, green. And this will be T alpha 2. Okay, we want to put the third one on there. Blue. And that will be the T alpha 3. Okay, and now we're going to put one more on, and that's, let's go back to that color. Okay, I'm going to go down here, and this was my T test value, which was calculated previously. Now I get a plus, so I can do it here. Let's see, y equals 3, just so you can see that command. And now let's see what happened. And this isn't what we wanted, but it's instructive. The horizontal axis only goes out to 2. Well, I told R 2.75, but it has a mind of its own when you give it the command pretty. And I thought those values looked okay, but I guess it didn't check all of them. And we can see one red line for the first critical value, the green line for the second critical value. We're not seeing anything else. So how do we fix it? We go back and change X. So with that change, when I told X, I gave it the R command pretty, and it went from 0 to 3. at 50 points. R seemed to like that a little bit better. And so now we have all the graph out with the interesting results. This is a T example. That's a T distribution curve. Doesn't look that different from a normal distribution, but you had to specify degrees of freedom in order to get it. It always has to be normalized, so you have to take your T value and your mean for your data and change it into a T test value. And it was 2.9, not 2.41. I saw it wrong. In this case, at all confidence levels, the null hypothesis would be rejected. So this is a conclusion of using R for hypothesis testing.